Welcome back to the Deep Dive. We're the show that tries to get straight to the core insights from, well, pretty complex research. Today we're jumping into the world of large language models. Their advancements feel almost like magic sometimes, right? But there's this constant challenge, this frustration almost, for researchers, really understanding why some designs work better than others. It often feels less like engineering and more like feeling your way through a dense fog.
Absolutely. It's a space where the empirical results, what we see working, often outpace our actual theoretical grasp. We know what works, sometimes, but the why is often missing. That leads to a lot of, frankly, guesswork and expensive trial and error in architecture design.
And that's exactly what we're digging into today. We've got this really interesting paper, Physics of Language Models, Part 4.1, Architecture Design and the Magic of Canon Layers. It's by Zeyuan Allen-Zhu from FAIR at Meta. What's exciting is that it proposes a new framework, a new way to think about understanding these models, and introduces this surprising component called Canon Layers, all aimed at making LLM design a bit less mysterious.
Yeah, so our mission here is really threefold. First, unpack the big hurdles researchers face in understanding LLM architectures. Second, reveal the novel approach this paper puts forward to tackle those hurdles. And finally, get into the details of these canon layers. How they function, their impact on different model types, and what it all suggests for the future of designing these systems. For you, our listeners, who are already experts in ML, data science, and math, this should be a pretty comprehensive look, giving you the key findings straight from the paper.
Okay, let's dive in. First up, the challenges. The paper calls the current situation the unreliable compass, which I think is a great phrase for why it's so hard to compare LLM architectures effectively. Challenge number one, they point out, is relying on pre-training loss as a good measure of, well, intelligence.
Right, and this is a big one. We often look at metrics like perplexity or cross-entropy loss. They're standard. But the paper argues they don't really capture real-world abilities reliably. You see, natural language data is inherently skills mixed. It's got simple memorization, multi-step reasoning, factual recall, all jumbled together. A model might get a great perplexity score simply because it's gotten really good at, say, memorizing common word sequences, not because it's actually reasoning better.
Ah, okay. So it's like a student who's great at multiple choice because they recognize keywords, but can't write an essay demonstrating deeper understanding. The paper gives an example with state-space models like Mamba, right?
Exactly. Mamba architectures can often hit very low perplexity scores quite early in training. They're efficient at that kind of rapid memorization. But as the paper points out, this early success on perplexity doesn't always translate into strong performance on complex reasoning tasks later on. They might nail the surface patterns but struggle with the underlying logic.
That sounds like a real trap if you're using these scores for things like early stopping during training or deciding which architecture is fundamentally better.
It absolutely is. If you stop training just based on perplexity, you might accidentally favor models that are just good at memorizing the training data's quirks, rather than models that are slowly building up more robust, generalizable reasoning abilities. The paper really emphasizes how this can lead to misleading comparisons. You might think architecture A is superior based on its loss curve, but it might lack the core skills needed for the tasks you actually care about.
Makes total sense. Okay, let's move to the second challenge, noise below emergent thresholds. We hear a lot about emergent abilities, these complex skills, maybe multi-step reasoning or complex instruction following, that only seem to appear when models get really big. We're talking, billions of parameters, trillions of tokens.
And that scale is precisely the issue for a lot of academic research. When you're working at more typical academic scales, maybe 1.3 billion parameters, 100 billion tokens, something more manageable. The paper finds that any real differences between architectures often get drowned out by noise. You might see a 2% improvement in accuracy, but it could just be random chance, a different data shuffle, a different initialization seed. It's not necessarily a signal of true architectural superiority. They even show, I think it was figure 1, accuracy swinging by 2-4% just from random seeds and 1-2% between different models.
Wow. So any small gain you observe might just be a phantom, leading researchers down potentially unproductive paths. But they say it's even more fundamental that at these scales, models can fail really simple reasoning.
That's right. They give a stark example, a basic two-hop reasoning question. Something like, X was born in 1970, Y has the same birth year as X, when was Y born? At these academic scales, the paper notes, models often just guess randomly. There's this fundamental floor where basic reasoning just isn't reliable. And this floor completely masks any potential architectural differences in how well models might handle more complex reasoning if they could get past that basic level. It makes rigorous comparison incredibly difficult, and doing the necessary large-scale experiments at industry levels to see past this noise is prohibitively expensive. It really hampers systematic scientific progress in architecture design. You end up relying more on heuristics than solid evidence.
Yeah, that paints a challenging picture. And the third challenge they discuss, grokking, data quality, and curriculum learning, suggests that sometimes the problem isn't even the architecture, but the data itself.
This is a really critical point. The paper talks about grokking, this weird phenomenon where a model suddenly generalizes or understands a concept, but only after a really long period of training, seemingly much longer than should be necessary. This often happens when the training data lacks enough challenging examples or maybe enough examples of intermediate difficulty. Imagine trying to teach 3-hop reasoning with only 1-hop and 3-hop examples. The model might struggle to bridge the gap and only get it after seeing tons of data almost by chance.
Which makes the whole training process very sensitive to randomness and the specific data mix, right? Further muddying the waters when you're trying to compare architectures. The paper mentions RL-based methods like GRPO or PPO, trying to fix this by feeding the model tailored data.
Exactly. Those methods try to provide data at the right difficulty level to nudge the model along, but they introduce their own confounds. Once you add a sophisticated RL fine-tuning phase, it becomes really hard to tell. Is the final performance due to the base pre-trained architecture, or is it the RL algorithm, or just some complex interaction between the two? It makes isolating the inherent strengths of the architecture itself very difficult. You get results, but you're not sure what they're truly telling you about the underlying design.
Okay, so we've got this landscape. Unreliable metrics, noise obscuring results at feasible scales, data issues causing unpredictable learning. It sounds like a tough spot for systematically improving LLMs. So how does the paper propose cutting through this? They introduce this idea of the synthetic playground, which sounds intriguing. It starts with atomic decomposition of intelligence.
Right, this is their core solution. To get around the noise, the cost, the unreliability of real-world pre-training, especially when models at academic scale can't even reliably do 2-hop reasoning, they say, let's break down intelligence into more fundamental, measurable pieces. Think of them as atomic components. Things like reasoning depth. How many steps can it chain? Reasoning breadth. How many dependencies can it handle at once? Knowledge capacity. How much can it store efficiently? And understanding a hierarchical structure.
And the key is using synthetic data, creating specific, controlled tasks to measure just one of these components at a time.
Precisely. By designing these synthetic pre-training tasks, they can evaluate each atomic component in isolation under really clean, idealized conditions. This minimizes all those confounding factors, the mixed skills in real data, the randomness, the data quality issues. It gives a much clearer signal.
They use a physics analogy like Galileo's Pisa Tower experiment.
Yeah, it's a great analogy. In physics, you use idealized setups, maybe a vacuum chamber or a frictionless surface, to strip away confounding variables like air resistance or friction, so you can see the underlying physical principles clearly. These synthetic tasks do the same for LLM architecture. They remove the noise of real-world data to enable clean, controlled, apples-to-apples comparisons. We can finally isolate and measure specific architectural strengths and weaknesses for specific capabilities.
Okay, let's connect that back. How does the synthetic playground address those specific challenges we outlined? Challenge 1 was the unreliable pre-training loss.
With the playground, you're doing single skill evaluations. So instead of looking at one messy overall perplexity score, you can directly measure how well does architecture A do on 5-hop reasoning compared to architecture B. You're measuring exactly the skill you care about, minimizing the risk of being misled by performance on easier, unrelated parts of the data mix.
Got it. And challenge 2, the noise below emergence thresholds. How does synthetic data help there?
It helps massively by lowering the resource requirements. Because you can generate essentially infinite, high-quality data perfectly tailored to the skill you're testing, even smaller models, sometimes as small as GPT-2 small, they mention can actually develop and demonstrate these complex skills, like deep multi-hop reasoning. This means you can spot architectural limitations and study mini-scaling laws much faster and cheaper than trying to do it with giant models on real data. Capabilities that might only emerge at massive scale in the wild can become visible much earlier in the synthetic setting.
That's a huge advantage for research iteration. And finally, challenge 3, grokking and data quality issues.
The playground tackles this head-on by giving you full control over the data difficulty distribution. You can ensure there's a smooth progression with plenty of intermediate complexity examples. This leads to much smoother learning curves and helps these advanced skills emerge more reliably and earlier, unlike the unpredictable grokking you might see with real-world data. It gives you a much clearer, more predictive insight into an architecture's inherent potential to scale and learn complex tasks, assuming future training pipelines improve.
This really does sound like a much more principled way to approach architecture comparison. So let's talk about these 5 specific synthetic tasks they designed. They call them DEPO, Brevo, Capo, Mano, and Lano. Let's start with DEPO for mental reasoning depth.
Okay, DEPO is designed to test K-hop reasoning, specifically over directed permutations. The key here is it requires internal computation, no chain of thought allowed. The model can't just talk its way through the steps. The format is pretty neat. You give it a chain of links, like by 1 points to y1, by 2 points to y2, and so on, up to xn points to ein. Then you give it a query, like query k1, q1, asking, what's the kth node starting from q1? The model has to output the answer a1 directly. It has to do those k steps in its head.
Then they have different versions, DEPO 1 and DEPO 2.
Yeah, they ramp up the difficulty. DEPO 1 uses short 1 to 2 token node names, maybe from a vocabulary of 50, and tests up to k8 hops. DEPO 2 makes it harder with longer 5-7 token node names, though from a smaller vocabulary of 4, and pushes the reasoning depth needed up to K16. They evaluate mainly on the hardest cases, like maximum hops, KK, but also intermediate steps, KK2, to see how the skill develops.
Okay, next is Brevo for mental reasoning breadth. This sounds like handling multiple things at once.
Exactly. Brevo tests the ability to process multiple dependencies simultaneously. Think about traversing a directed acyclic graph, or DAG. Like answering, who are Alice's nephews? You might need to follow multiple family branches concurrently, or some math word problems require tracking several pieces of information.
So a DAG is like a flowchart with no loops. You can always move forward.
Right. And the format for Brevo is by 1 depends on y1.xm, depends on emonu sc ans a1a. The model needs to output all the nodes that are reachable from the query node queue, but in topological order, meaning prerequisites first. It's a real test of mapping out interconnected information globally. And they mention a key insight from another paper. Models seem to have to process the entire DAG structure mentally before they even generate the first output token. This confirms it's really testing that global processing breadth. Again, there's Brevo 1 with single token nodes and Brevo 2 with multi-token nodes for more complexity.
Interesting. Then there's Capo for knowledge capacity. This sounds like measuring how much stuff a model can memorize efficiently.
Pretty much. It measures the efficiency of storing factual knowledge directly in the model's parameters, essentially bits of information stored per parameter. They use synthetic biographies for this, things like birth dates, universities, jobs presented in lots of different paraphrased ways to force actual understanding, not just surface matching. And critically, they evaluate this in an undertrained regime. Each fact is only shown about 100 times. This limited exposure is designed to really highlight differences in how efficiently different architectures encode information. If you train forever, maybe any architecture can memorize, but this tests the speed and efficiency of that encoding. The datasets range from storing a few million bits up to 100 million bits.
Okay, after capacity comes Mono for knowledge manipulation. So not just storing facts, but doing something with them.
Precisely. Mano tests retrieving stored knowledge and then performing computations on it, specifically hierarchical computations. They use synthetic modular arithmetic problems like AB plus CD mod 23. Again, no chain of thought is allowed. The model has to implicitly learn the 23 by 23 multiplication and subtraction tables, retrieve the right values for A, B, C, D, and then perform the multi-step calculation internally. The difficulty scales with the length L of the expression, going up to L16.
And the last one is Lano for hierarchical language structure. This sounds like it gets at the core of understanding grammar and syntax.
It does. Lano uses synthetic data generated from context-free grammars, CFGs, but with a twist: token-level ambiguity. This means just looking at nearby words isn't enough to understand the sentence structure. The model has to use global context and perform something like dynamic programming to figure out the correct parse. For the technically minded, this requires effectively an ON3 complexity operation relative to sentence length and hen. They use datasets with increasing complexity and length up to 1,000 tokens, CFG3K. Evaluation involves checking if the generated output is grammatically valid according to the CFG and how closely its token distribution matches the ground truth. It's really testing if the model has learned the underlying recursive rules of a complex language.
Oh, okay. That's a comprehensive set of synthetic benchmarks. So with this playground established, the paper does an initial comparison of some standard architectures. This is still part of their Result 0. They looked at transformers like Llama, with rope and a no-P version, linear attention like GLA, and recurrent state space models like Mamba 2.
Right. And they were careful to standardize model sizes and training setups to make the comparison as fair as possible initially. They deliberately avoided complex hybrid models at this stage to really isolate the behavior of these core families. The initial results, shown in their figure 4, suggested a pattern. GLA seemed the weakest overall. Mamba 2 showed strengths in the knowledge-based tasks, Capo and Mono, and Llama, especially the Rope E variant, looked best on the reasoning tasks Depot, Brevo, and Lano.
But, and this seems like a huge but, they immediately follow this up with a massive caveat. They say this initial comparison is incomplete and actually unfair. This is the Pisa Tower moment you mentioned.
Exactly. This is the crucial insight that reframes everything that follows. They point out that Mamba 2 has a built-in conv1d 1D convolution operation as part of its block structure. This conv1d, as they'll show later, acts very much like one of their Canon layers. The vanilla Llama and GLA models they compared it against didn't have this component, so they weren't comparing like with like. Mamba had this hidden advantage, this Canon-like feature already baked in. The initial comparison was skewed.
Ah, okay. So the later results, where they add Canon layers consistently to all architectures, will be the truly fair comparison.
Precisely. This discovery itself is significant because it suggests we might have been misattributing the performance of some architectures, not realizing a key component was playing such a crucial role. It sets the stage for introducing Canon layers properly.
Right, this is where it gets really interesting. Let's talk about the magic of Canon layers and this idea of horizontal information flow. What exactly are Canon layers?
So Canon layers are fundamentally lightweight architectural pieces designed to help information flow horizontally between adjacent or nearby tokens in a sequence. The name comes from music, like a musical canon where a melody repeats slightly offset in time, creating these overlapping horizontal patterns. The idea is to efficiently mix local contexts.
And they solve a specific, maybe surprising, inefficiency in standard transformers. Some think about needing multiple layers for simple tasks.
Yeah, it's quite counterintuitive. The paper points out that a standard transformer can be weirdly inefficient for basic things like associative recall. Sometimes it takes 2 full attention layers just for information to get from one token to its immediate neighbor. As the paper puts it, it's like shooting a bird with a cannon, using this heavy, global attention mechanism for a very local information passing task. A single attention layer might need a huge hidden dimension just to remember a sequence, while 2 layers can do it with a much smaller dimensions because that first layer is effectively just doing the job of reading the neighbor. Canon layers offer a direct, lightweight fix for this. They compute a weighted sum of the current token's representation and its immediate predecessors. Formally HT, but W0000 plus W1 plus W task W3 plus W3 art HT of U plus W3. The weights, W0 to W3, are learned, allowing the model to figure out the best way to blend local context efficiently.
Okay, and how flexible are these? Can you just slot them in anywhere? They show different integration points in figure 6.
They're quite flexible. You can place them strategically within a standard transformer or linear model block. Canon A goes before the main attention SSM block. Canon B goes inside the block, often applied to the query, key, or value projections in attention, or within the SSM calculation. Canon C goes before the MLP feed-forward layer, and Canon D goes inside the MLP layer. They refer to using all 4 as full-score Canon, ABCD, but they also test various combinations. This modularity is key because it lets you systematically test where this local mixing provides the most benefit.
And implementation-wise, are they heavy? What's the overhead?
That's one of the most appealing aspects. They're incredibly lightweight. The paper mainly uses a trainable 1D causal convolution with a small kernel size, like 4. They leverage efficient CUDA implementations, so the compute overhead is minimal. Crucially, they stress the use of an explicit residual connection. HT equals HT plus conv1d. This plus HT part is vital. It helps stabilize training and allows the main representation to easily incorporate the local adjustments from the convolution. And the parameter increase is tiny, less than 0.5% for GPT-2 small, and something like 0.0063% for a 1.3 billion parameter llama. Even with all 4 canons, ABCD, it's almost negligible.
That's remarkable. Such a small addition for potentially big gains. Does this connect to things people have tried before?
Yes, they connect it to earlier ideas. For instance, simple uniform attention, just averaging the last few tokens, worked surprisingly well on some tasks. Canon layers are like a learned, more sophisticated version of that local averaging. They also explicitly acknowledged the conv1D operations found in models like Mamba and GLA, often linked to the H3 shift SSM idea. Those typically resemble a Canon B, often without the crucial residual connection and maybe with an activation.
But the paper's contribution is broader.
Exactly. Their work generalizes this idea. They systematically evaluate this learned local mixing, the Canon layer, across all types of sequential models, transformers, GLA, Mamba, and all potential locations within the block. A, B, C, D. They demonstrate that the benefit isn't tied specifically to attention or SSMs. Canon layers work more generally to improve local information flow, acting as a fundamental building block.
Okay, let's see them in action. Canon layers in action. Boosting transformers. Result 2 in the paper, figure 7, they talk about dramatic performance boosts for models like Llama with that tiny parameter increase.
The results are pretty striking for transformers. Let's take reasoning depth, depot. Vanilla Llama with Rope E really struggled here, often hitting a wall around capo 4 hops. Add Canon layers, ABCD, and suddenly it's getting over 50% accuracy at K8 and near perfect at K16 on the harder Depot 2 task. It's a massive leap in multi-hop reasoning ability.
So it's not just a small improvement, it's like unlocking a capability that was latent or just too hard to learn before.
That's exactly how it seems. It's about accelerating the learning of these deeper hierarchical computations. Canon layers help the model master the simpler steps, 1-hop, 2-hop, much more efficiently, which then allows it to progress to deeper reasoning faster. It might not change the theoretical maximum depth achievable with infinite data, but it dramatically speeds up skill acquisition, making complex reasoning emerge much earlier and more reliably.
What about reasoning breadth?
For reasoning breadth, Bravo, they see roughly a 30% improvement. A Rope E model with Canon layers can handle problems like Brevo 1 N90 or Brevo 2 N40 that a vanilla Rope E model could only handle at lower complexities, N70 or N30 respectively. It suggests Canon layers help process those local dependencies needed for navigating the graph structure more effectively.
And for the knowledge tasks, capo and mano.
On knowledge capacity capo, there's a solid 10-15% increase in effective capacity in that tough, undertrained regime. 100 exposures. This is interesting because gated MLPs, like in Llama, were known to slightly hinder knowledge acquisition speed. Canon layers seem to counteract that, recovering about half the capacity loss by improving the overall training dynamics.
Okay, so they help make up for a known downside of gated MLPs.
Exactly. And for knowledge manipulation mono, the improvement is around 30% in the complexity length L the model can handle. A Rope S Canon model working on L13 expressions performs as well as a vanilla Rope E on simpler L10 expressions. Again, it points to faster learning of the hierarchical steps involved in the computation.
And the language structure task, Lano.
Significant improvements there too, especially on the challenging CFG3K dataset. Rope E plus Canon models could handle roughly twice the structural complexity compared to vanilla Rope. Across the board, Canon layers provide substantial, consistent gains on all these diverse tasks for transformers without causing instability.
Now this next finding sounds almost too good to be true. Reviving no-P in result 3. Transformers without any positional embeddings, which are usually terrible, become strong performers with Canon layers.
It's genuinely one of the most surprising results. No PE models, starting from near zero accuracy on many tasks because they have no inherent sense of word order, are transformed by Canon layers. They don't just become usable, they often match or even beat the Row P plus Canon models, especially on reasoning depth. And compared to other fixes for no P, like alibi or H alibi, the paper shows no P plus Canon performs significantly better. Figure 10, top. It suggests Canon layers provide a much more fundamental mechanism for injecting the necessary local relative positional information than these other methods.
That's incredible. And it also means less reliance on ROPE itself, which has issues with generalizing to long sequences.
Precisely. A major implication is that with Canon layers present, you often don't need full rope applied across all the hidden dimensions. In fact, the paper finds that a reduced rope applied to only 14 of the dimensions, they call this rope plus Canon, often performs better than both full rope plus Canon and no PP plus Canon. This is great news for handling long contexts because rope scaling can be problematic. Canon layers let you get away with less rope, improving length generalization.
Okay, to really understand why this works so well, they did ablation studies, result 4. What did they find about the different Canon components, A, B, C, D?
They found a clear cumulative benefit. Each component adds something. Adding just one Canon layer helps. Adding more helps more, especially for weaker baselines like no-P. It shows the modularity works, you can stack them.
And the residual connection, you said it was vital. Why again?
The HT plus part in the definition HT plus conv1d is critical. It's not just for stability, though it helps there too. It allows the main information pathway HT to remain intact, while the Canon layer provides local corrections or enrichments. Without the residual, information flow gets disrupted, training is much slower and less stable, and the final performance is significantly worse, as seen in their NORS ablations in Figure 10. It's key for integrating the local and global information smoothly.
Are Canon layers tied to the attention mechanism or the MLP?
They seem largely independent. They showed that Canon ACD, Canon's before attention, before MLP, inside MLP, works really well. Even without modifying attention at all, Canon B is absent. Similarly, other combinations work too. It really reinforces the idea that Canon layers are a general-purpose enhancement for local information flow, not something intrinsically linked to just attention or just MLPs.
And adding nonlinear activations like Zeyuan after the Canon convolution, did that help?
Nope, they found no noticeable benefit from adding activations like Zeyuan right after the Canon layer. The necessary nonlinearities seem to be well handled by the main attention MLP blocks that follow. It keeps the Canon layer design simple and efficient.
Let's look at how Canon impacts MLP choices and mixture of experts MOE models. Result 5. First, gated versus standard MLPs.
So gated MLPs, like in Llama, do tend to be slightly better on reasoning tasks, especially mono knowledge manipulation. But as we noted, they can slightly slow down knowledge acquisition, capital capacity. Canon layers help here by recovering about half of that lost knowledge capacity, making gated MLPs more attractive overall as you get the reasoning benefits with light of the capacity drawback.
And for MOE models. They're popular for scaling, but can be slow learners.
Right. MOE models often learn knowledge more slowly. There's a slight conflict. Canon D, inside the MLP, doesn't play well with MOE because MOE routes tokens to different expert MLPs independently. However, using Canon ABC before attention, inside attention, before MLP, significantly accelerates knowledge acquisition in MOE models. It improves their bit per parameter efficiency, recovering at least half of the typical MOE capacity slowness. So Canon layers can make MOE models learn faster, even if you avoid placing them inside the MOE router itself.
They also looked at squared ReLU2.
Briefly, ReLU2 showed very minor gains on standard MLPs, nothing compared to Canon layers, and applying it to gated MLPs actually hurt performance. So again, Canon layers seem like the much more impactful and robust enhancement.
Okay, shifting gears now to Canon layers in action, transforming linear models. Gated linear attention, GLA, started as the weakest baseline, but result 6 shows Canon layers turn it into a strong contender.
It's a remarkable turnaround. Adding Canon ABCD transforms GLA. Suddenly, its reasoning depth jumps from just 1 hop to 4 hops. Its reasoning breadth doubles. Its knowledge manipulation ability more than doubles in terms of complexity handled. What's really striking is that GLA plus Canon becomes competitive with, and sometimes even surpasses, Mamba 2, especially on the Brevo 1 task. This is huge, showing Canon layers can unlock potential in simply linear architectures, compensating for their inherent limitations in local context processing.
And the GLA ablations, result 7, confirm this.
They do. GLA actually had its own built-in conv1d, like a partial Canon B, but the paper shows this provided almost no benefit on its own. It didn't help reasoning and slightly hurt knowledge manipulation. The key finding, just like with transformers, was that the residual connections on the Canon layers were essential. Full Canon ABCD with residuals is what unleashed GLA's performance.
This leads directly to the bombshell claim in result 8, Mamba's secret revealed.
They argue Mamba 2's success wasn't primarily the SSM formulation itself. That's the core argument, and it's backed by strong evidence. They propose that Mamba 2's strong performance comes largely from its built-in auxiliary conv1d operation within each SSM block, an operation that functions essentially as a partial Canon B layer.
So the magic was this convolutional part. What happens if you take it out of Mamba?
The performance plummets. If you disable that internal conv1d, Mamba 2's performance drops dramatically, basically down to the level of the original weak GLA baseline. This holds true on both the synthetic tasks and real-world benchmarks. It strongly suggests this Canon-like conv1d component, not the core state space mechanism, was the main driver of Mamba 2's observed effectiveness. It really challenges the narrative around why Mamba works so well.
Wow. But even knowing this, adding full Canon layers still improves Mamba.
Yes, quite significantly. Replacing Mamba's built-in conv1d with the full Canon layer setup, like Canon AB or Canon ABCD depending on the variant, consistently improves Mamba's performance further, especially on tasks like mono, knowledge manipulation, and Brevo, reasoning breadth. It shows that even though Mamba had a piece of the puzzle, the full systematically applied Canon layer concept offers additional benefits, highlighting its general power.
They did more Mamba ablations too, result 9, looking at residuals and sublayers.
Right. For Mamba, the effect of Canon residual links was mixed. Disabling the residuals sometimes helped on mono and brevo, Mamba's strong suits, while enabling them helped on llano and depo, recursive reasoning. So the optimal choice might depend on the task focus. Adding more Canon sublayers generally helped Mamba even when placed outside the main SSM block, like Canon ACD on a variant with a separate MLP. This again shows Canon's generality. It helps improve horizontal flow regardless of the main computational block it's attached to.
And that mimetic initialization for Mamba meant for length generalization.
In their synthetic tests, it provided no measurable benefit and sometimes even hurt performance on other tasks. It's another example highlighting why testing across a diverse set of capabilities is crucial. Optimizing for one thing might compromise others.
Okay, so after systematically adding Canon layers everywhere, fixing the MambaCon V1D issue, we finally arrive at the new landscape, a controlled architectural comparison. Result 10, figure 15. This is the fair comparison, the leveled Pisa Tower. What does it show?
Exactly. Now we can make scientifically meaningful comparisons. Here's the breakdown. Reasoning depth. Rope, with reduced Canon and no P, are clear winners, achieving about 2x deeper reasoning than Mamba 2 and GLA, which are roughly equal. Attention still rules here.
Okay, reasoning breadth.
Rope E, reduced Canon, is slightly ahead, followed by no P, Mamba 2, and GLA, all performing similarly.
Knowledge capacity, where Mamba initially shown.
Here, Mamba 2 and GLA maintain a slight edge over the Rope E and no P variants. So linear models seem slightly better at raw storage efficiency, even with Canon.
Knowledge manipulation.
Mamba 2 is roughly on par with or slightly better than Rope E, reduced Canon. No PE and GLA lag a bit. So Mamba holds onto an advantage in manipulating stored facts.
And hierarchical structure, llano.
Rope E, reduced Canon, is again the leader here, clearly outperforming No PE, Mamba 2, and GLA, which are all similar. So the final picture is clearer. Transformers, Rope plus Canon, excel at deep hierarchical reasoning. Linear models, Mamba GLA plus Canon, have an edge in knowledge capacity and manipulation. The trade-offs are now much more evident.
This leads right into result 11, the Achilles heel of linear models, figure 16. What's the fundamental limitation this study identifies for models like Mamba and GLA?
The paper is very direct. Linear models consistently struggle with deep reasoning. Even simple 1- or 2-hop retrieval tasks become unreliable. It's not that they can't store the information, their capacity, capo, is fine. The problem lies in the efficiency and reliability of compressing in-context information and then retrieving and integrating it over multiple steps. Errors accumulate quickly as the reasoning chain gets longer. This inefficiency in multi-step information processing seems to be their core weakness.
That pinpoints a really specific area for future research in linear model design then.
Absolutely. And practically, it suggests that for now, hybrid models might be the way to go. Maybe use efficient attention, like sliding window for handling the deep reasoning parts, and linear SSM components for efficiently managing very long contexts. And importantly, the paper implies both components would likely benefit significantly from having Canon layers added.
Finally, they take these insights back to the real world, validating them with academic scale pre-training. Result 12, figure 17. What was the setup?
They trained 1.3 billion parameter models, a common academic size, on 100 billion tokens. Fine Webby Edu, Slim Pajama, context length 4096. Pretty standard stuff. They evaluated using standard discriminative benchmarks, PIQA, HelloSwag, ARC, etc., via Elm-Evil harness, and also generative tasks, like question answering on SWDE, FDA, Squad, using a specific protocol called Just Read Twice, JRT, to help smaller models perform better on generation.
And they still acknowledge noise even here.
Yes, they highlight that even at this scale, random seeds cause significant variability, up to 9% swings on some tasks. It reinforces their point about the difficulty of getting clear signals from academic scale pre-training alone. Only large differences are truly meaningful.
So, did the real-world results generally align with the synthetic playground findings?
Yes, largely they did. Key observations. First, the linear models, Mamba 2, GLA, significantly underperformed the full transformers, especially on those retrieval-heavy generative tasks. This matches the synthetic finding, result 11, that their weakness is in compression retrieval, not just raw memory over long context.
Okay, that matches. What else?
Second, and this is a stark confirmation, even the simplest 2-hop reasoning tasks failed. All models perform near random chance, 30-36% accuracy. This directly validates the synthetic playground's finding about the noise floor and the unreliability of multi-hop reasoning at this 1.3B scale. You simply can't differentiate architectures based on skills that haven't reliably emerged yet.
So 2-hop fails, but what about 1-hop?
One-hop tasks, like basic fact recall, did show the full transformers outperforming the linear models, suggesting a difference even in single-step retrieval reliability. And finally, the length generalization predictions held up. No PE models and transformers with reduced rope, ROP-S Canon, showed better performance on long context tasks, like one-hop-L and Babylon, compared to full rope models, confirming the synthetic insights.
All right, let's wrap this up. This paper, Physics of Language Models, Part 4.1, really tackles the messiness of LLM architecture research. It argues academic scale pre-training is too noisy and often doesn't even allow complex reasoning to emerge, making comparisons unreliable. Their solution is the synthetic playground, breaking intelligence into atomic tasks for clean, controlled, cost-effective evaluation.
And through this lens, they introduce and validate Canon layers, these simple, lightweight components for horizontal information flow. They show these layers provide dramatic boosts across the board. They revive models like NoPE and GLA, make transformers better at length generalization by reducing rope dependence, and crucially, they pinpoint the real weakness of linear models as being inefficient multi-step information retrieval, not just memory capacity.
The implication seems to be that Canon layers could become a standard fundamental building block in element design, maybe like residual connections or layer norm. For you, our expert audience, this research offers really specific insights into architectural trade-offs. It gives a clear view of where different families excel and struggle.
Exactly. It provides a data-driven basis for focusing future innovation. How can we better address the deep reasoning bottlenecks in linear models? How can we best leverage Canon layers across different architectures? As training data and methods improve, using these kinds of controlled synthetic evaluations, informed by findings like the power of Canon layers, seems crucial for guiding the development of genuinely smarter, more capable models, not just bigger ones.
A fascinating look at bringing more physics-like rigor to the art of LLM design. That's our deep dive for today. Thanks for joining us. We'll be back soon with another exploration of cutting-edge research.